we will be exploring the remarkable improvement in process control, health maintenance that have defined the historic campaign of uh, AHMSA, one of the Mexico's largest integrated steel plant, BF5 story. This presentation will detail how strategic enhancement led to significant increase in production productivity and a record-breaking campaign life. Blast furnace number 5 HMSA largest has been in its third campaign since August 1994. A key challenge for AHMSA is the quality of its raw material, which have high level of alkalis and zinc in iron ore and high ash and sulfur in injection coal. Despite these challenges, this campaign has achieved a record-breaking hearth life, producing over 32.5 million tons of hot metal and is still in operation. As you can see, the statistics of BF5 is a significant asset with a hard diameter of 11.2, a bellless top charging system, and it uses granulated coal as its primary fuel. So, how did they achieve this? A series of strategic improvements were key. The granulated coal injection system or GCI was upgraded to support higher production level. Oxygen enrichment was increased to maintain stable flame temperature. Crucially, in 2007, an advanced expert control system was installed to automate process control, and as we will see, a specialized hearth maintenance using material like ilmenite and synthetic TiO₂ becomes critical for extending the furnace life. The impact of these changes was dramatic. Production capacity increased 5,500 to 6,550 metric ton per day, and productivity jumped from 2.5 to 3.1 ton per day cubic meter. The, the statistics clearly shows the impressive upward trend in both production and productivity over the campaign. Let's look closer at the process control. The VAI Expert System or XPS operate in a closed loop over 97% of the time, meaning it automatically send recommendation to the furnace control system. It integrate sophisticated models for burden control, hearth wear and energy balance. The primary benefit of this system was a dramatic improvement in stability. As the graph shows, both the hot metal temperature and its silicon content become much more consistent after the XPS was implemented, which is a crucial for high quality steel production. One of the biggest operational challenge was the formation of scabs or buildups on the furnace wall caused by high level of fines and alkalis in the raw material. The old strategy involved charging high volume of coke to the furnace wall to keep temperature high. However, XPS burden model enabled a completely new approach. The new strategy reduced coke at the wall to lower the gas temperature, which prevent scabs from forming. Instead, gas flow was directed more toward the center to blow out the harmful alkali and zinc. This involved adjusting coke layer, increasing wear velocity, and optimizing the burden distribution profile. And this gives a result. Gas utilization increased significantly from around 48 to over 51%, leading to a better permeability and allowing for higher blast volume, which in turn boosts production. Managing the high alkali content from the raw material was essential for a stable operation. The goal was to remove at least 80% of these alkalis through the slag. To achieve this, the team adjusted the slag chemical composition as the slag basicity was modified to promote alkali elimination. A key change was reducing the MgO content in the slag from over 16% down to 7.5%, which lowered its melting point. These this adjustment allowed the furnace to operate stably even with a high alkali input of over 5.5 kg per ton hot metal. Perhaps the most incredible part of the story is the extension of the hearth life. Designed for 20 million tons, it has now produced over 32.5 million. Back in 2000, the hearth showed severe significance of wear, including gas leak and iron infiltration threatening the entire campaign. A dedicated team implemented a comprehensive hearth care program. This included improved casting practices and strategic use of titanium. They began charging ilmenite and injecting titanium fines, but found that synthetic TiO₂ called Rutilit was far more effective for treating hot spot. Rutilit F50 is now used to treat a specific hotspot when temperature exceeds 600 degrees Celsius, while a blend is used continuously to maintain wall temperature between 300 and 500 degrees Celsius. The chart clearly shows how TiO₂ injection successfully brought down temperature at the iron notch, safeguarding the furnace. To summarize, AHMSA blast furnace number 5 stands as a testament to the power of integrated improvement. They achieved higher production through enhanced process control, particularly with expert system. They managed poor raw material quality by adjusting slag chemistry, and most importantly, they achieve a record-breaking campaign life through a dedicated scientific approach to hearth maintenance. Looking ahead, HSMA, AHMSA plan further upgrades including new cast house equipment and a stove reconstruction to continue pushing the boundaries of performance.